the construction of bridges has evolved significantly over the centuries, adapting to the demands of modern infrastructure and the need for innovative materials. A landmark project in this evolution is the Bridge, innovative road bridge made from FRP composites, completed by Mostostal Warszawa in 2015. This project not only marked the construction of Poland's first road bridge using fiber-reinforced polymer, FRP composites, but also set a world record for the longest span of its kind. The birth of an innovative project, the Bridge project was born from the need to explore and develop new construction materials that offer superior performance compared to traditional options like steel and concrete. The project was executed by a consortium led by Mostostal Warszawa SA, a company with a long-standing reputation in the construction industry. The consortium also included Promost Consulting T.Cwawski Spółka Jana, responsible for the bridge design, the University Research Center for Functional Materials, which conducted material research, and Rzeszów University of Technology, which handled structural testing. The project was co-funded by Poland's National Center for Research and Development under the Demonstrator Plus program, aimed at supporting innovative research and development initiatives. Why FRP composites? Fiber-reinforced polymer, FRP composites represent a significant advancement in construction materials. Comprising continuous fibers, such as carbon or glass, embedded in a polymer matrix like epoxy resin, these composites offer exceptional strength-to-weight ratios, corrosion resistance, and durability. These properties make FRP composites particularly suitable for bridge construction, where load-bearing capacity and longevity are critical. In the Bridge project, FRP composites were selected to fabricate the main structural elements, such as beams and reinforcements. The use of FRP allowed for the creation of a lightweight yet robust structure, addressing common issues like corrosion and the need for frequent maintenance, which are prevalent in traditional materials. The production process. The production of FRP composite elements for the bridge was a meticulous process. Mostostal Warszawa undertook the fabrication of all composite parts at its facility in Warsaw. The production process involved laying out multiple layers of carbon and glass fiber fabric, which were then infused with epoxy resin using a vacuum-assisted resin transfer molding process. This method ensures that the fibers are thoroughly saturated with resin, producing a high-quality, durable composite material. One of the most challenging tasks in this project was the creation of composite beams, each 22 meters long and weighing 3,700 kilograms. Despite their length, the beams were light enough to simplify transport and installation, reducing overall construction time and costs. The infusion process, which lasted about 8 hours per beam, required precision and control, as any mistake could compromise weeks of work. Structural testing and verification before the bridge could be installed. Extensive testing was carried out to ensure the structural integrity and safety of the FRP components. Rzeszów University of Technology's strength testing laboratory played a crucial role in these assessments. The testing involved simulating various load conditions and monitoring the response of the composite beams to identify potential weaknesses. One of the unique aspects of this testing was the use of acoustic emission methods, conducted by the Warsaw University of Technology, to detect and analyze internal defects in the composite materials. This advanced testing technique allowed for real-time monitoring of the structural behavior under load, providing valuable data for further refinement and validation of the design. Installation and assembly. The installation of the bridge in Blazowa, Rzeszów County, was a testament to the advantages of using FRP composites. The lightweight nature of the beams allowed for a quicker and safer assembly process. The installation of the beams took less than 2 hours, highlighting the efficiency gains compared to traditional materials. The bridge's load-bearing structure was further enhanced by using FRP composite reinforcement bars and a specially formulated lightweight concrete for the deck slab. The final step before commissioning the bridge involved a comprehensive load test to ensure it could handle the expected traffic loads safely. This testing was particularly rigorous due to the innovative nature of the materials used. Over 120 sensors were installed to monitor the bridge's response to loads, including the detection of any micro cracks or material degradation. The bridge was subjected to a static load of 180 tons, far exceeding the design specifications. The results confirmed that the bridge not only met but exceeded its designed load-bearing capacity. The structure demonstrated superior stiffness and strength, and the testing equipment proved inadequate to induce failure, highlighting the robustness of the FRP composite construction. The COM Bridge project stands as a pioneering achievement in the field of bridge construction. It showcases the potential of FRP composites to revolutionize infrastructure by offering a lightweight, durable, and maintenance-free alternative to traditional materials. This project has not only contributed to advancements in material science and engineering, but has also set a new benchmark for future bridge designs worldwide. The successful completion of this project underscores the importance of innovative thinking and collaboration in pushing the boundaries of what is possible in construction. In June 2019, CRL Concrete Repairs Limited successfully completed the supply and installation of two identical fiber reinforced polymer FRP composite bridges over watercourses in Ockwells Park for North Yorkshire County Council. These bridges were part of an infrastructure upgrade aimed at enhancing accessibility and durability in the park's pedestrian pathways. FRP composite bridges were chosen for their superior strength-to-weight ratio, corrosion resistance, and low maintenance requirements compared to traditional materials like steel or concrete. This made them an ideal solution for the park's natural environment, where exposure to moisture and varying weather conditions could degrade conventional materials over time. The installation process involved meticulous planning and execution to ensure minimal disruption to the park's ecosystem and visitors. The lightweight nature of FRP allowed for easier transportation and quicker installation, reducing the overall project timeline. Dancy's Pass, a notable and scenic route in the Waitaki district of New Zealand, faced significant disruption when Bridge 66, which carried the Dancy's Pass Road over the Mariwhenua River, was destroyed by flooding in June 2013. This route is crucial not only for local residents and farmers, but also for tourists who frequent the area for its rugged landscapes and historical sites. The loss of Bridge 66 created a pressing need to restore connectivity in this remote area quickly, prompting the Waitaki District Council to seek immediate assistance from the New Zealand Transport Agency, NZTA. The role of the NZ Transport Agency and Downer NZ. Understanding the urgency of the situation, the NZ Transport Agency responded swiftly to the Council's request by commissioning the installation of a temporary Bailey Bridge. Downer NZ, the agency's designated Bailey Bridge Services contractor, was tasked with the installation. Downer NZ has a reputation for effectively managing civil infrastructure projects, especially in challenging environments, making them an ideal choice for this rapid deployment. A Bailey Bridge is a type of portable, prefabricated truss bridge that was developed during World War II for military purposes. Its design allows for rapid assembly without the need for heavy machinery, making it ideal for emergency situations like the one at Dancy's Pass. The modular design of Bailey bridges allows for various configurations and lengths, depending on the requirements of the site, and they can be assembled manually by a small team, which is crucial in remote areas with limited access to resources. The installation of the Bailey Bridge at Dancy's Pass was completed in July 2013, a remarkable achievement considering the remote location and the logistical challenges posed by the environment. The process began with a thorough site assessment to ensure that the bridge could be installed securely and safely over the Mairi-Whenua River. Given the rugged terrain of Dancy's Pass, transporting the bridge components to the site was a challenging task. The components had to be delivered in sections and assembled on-site. Once at the location, the assembly team worked systematically, first constructing the supporting structure and then laying the bridge deck. The modular nature of the Bailey Bridge allowed the team to adjust the bridge's length to match the span of the river, ensuring that it was both functional and stable. The installation was not without its challenges. The team had to work under time constraints, and the weather conditions in Dancy's Pass, known for being unpredictable and harsh, added an additional layer of complexity to the project. Moreover, ensuring that the temporary bridge could withstand potential future flooding was a critical consideration. Engineers had to carefully design and position the bridge to minimize the risk of future damage, taking into account the river's flow and potential for further flooding. The successful installation of the Bailey Bridge restored essential connectivity to the Dancy's Pass Road, allowing residents, tourists, and service vehicles to use the route once more. The temporary bridge also provided the necessary time for the Waitaki District Council to plan and execute a more permanent solution without disrupting the flow of traffic. The Brinkman Bowden Plate Foundation Slab is an innovative and robust solution designed to serve as the foundational base for residential buildings. This foundation system is recognized for its stability, durability, and energy efficiency, catering to a variety of construction methods and building requirements. The foundation slabs are meticulously designed by a team of engineers who customize each slab to align with specific building plans, ensuring that the unique needs of each project are met. The slabs are constructed using high-quality, waterproof concrete W8 25/30, which is known for its strength and resilience. This concrete is combined with dramix steel fibers and traditional reinforcement methods, a process developed in collaboration with Baykart and a German engineering office. This combination results in a foundation slab that is exceptionally durable, capable of bearing heavy loads while maintaining a relatively thin profile. This structural integrity is a testament to the advanced technology and precise engineering that goes into each Brinkman Bowden Plate slab. A key feature of the Brinkman Bowden Plate slab is its energy efficiency, particularly its ability to maintain a stable temperature beneath the slab. This is achieved through the incorporation of a frost-resistant wall that is buried below the frost line around the entire slab. This design ensures that the temperature under the slab remains above +9 degrees Celsius, even in harsh winter conditions. This thermal stability not only enhances the energy efficiency of the building, but also allows for cost-saving measures, such as the omission of horizontal insulation under areas like garages, while still applying it under living spaces. To prevent thermal bridging between different areas of the building, a thermal break is installed between the garage and living spaces. The foundation slabs are also designed with varying thicknesses of insulation, tailored to meet different energy efficiency standards, including those of passive houses. One notable option is the heated slab, which integrates a water heating system directly into the slab. This system leverages the high thermal mass of the slab to reduce the energy required to maintain a comfortable indoor temperature, leading to significant energy savings over time. Preparation is crucial to the successful installation of the Brinkman Bowden Plate foundation slab. The process begins with a detailed geotechnical analysis provided by the client, which informs decisions regarding soil replacement and sub-base preparation. High-quality sand is selected for the sub-base to ensure ease and effectiveness in compaction, creating a solid foundation for the slab. The slabs are more than just concrete and steel reinforcement. They also include essential infrastructure such as plumbing, utility connections, and drainage systems. The perimeter drain system is particularly important as it removes excess water from around the slab and provides the option to store and reuse this water later. Brinkman Bowden Plate prides itself on efficiency, with the capability to construct foundation slabs up to 150 square meters in size within just 5 days. The company offers personalized service, inviting clients to request a free quote by providing their ground floor plans, building cross-sections, and geotechnical reports. In March 2014, the rapid installation of a temporary Bailey-style bridge by the Washington State Department of Transportation, WSDOT, in Thurston County, south of Olympia. This installation was a critical response to a structurally deficient bridge along Little Rock Road, which had been compromised and deemed unsafe for continued use. The Bailey Bridge provided a crucial temporary solution to restore local access while a permanent replacement bridge was planned and constructed. Bailey bridges, known for their modular and portable design, have been widely used in both military and civilian contexts for their efficiency in emergency situations. The installation process for this particular bridge was a collaborative effort between WSDOT and Thurston County crews. These teams worked together seamlessly, combining their expertise and resources to complete the project swiftly and effectively. The time-lapse footage spans 3 days, showing the entire construction process condensed into a brief visual summary. It begins with the initial preparation of the site, including the removal of any debris and the setting up of foundations to support the temporary structure. The modular components of the Bailey Bridge, which are prefabricated and easily assembled, were then transported to the site. Workers can be seen carefully piecing together the bridge, using cranes and other heavy machinery to position the large steel trusses. As the video progresses, it highlights the efficiency and precision of the installation process. Despite the challenging timeline, the crews were able to complete the bridge installation within the planned timeframe, ensuring that local residents and emergency services had restored access across the waterway.
Keisanuma Bay Cross Bridge, also known as Kanae Ohashi Bridge, is a remarkable structure that spans Keisanuma Bay in Japan. It is a significant component of the Sanriku Expressway, a 359-kilometer-long automobile-only road connecting Sendai City in Miyagi Prefecture to Hachinohe City in Aomori Prefecture, running along the coast of Iwate Prefecture. The construction of the Keisanuma Bay Crossing Bridge was a major project aimed at recovery from the devastating Great East Japan earthquake, which struck the region in 2011. The bridge was designed not only as a means of transportation, but also as a symbol of hope and resilience for the people of Keisanuma. Supported by 2 towering structures that rise 115 meters above sea level, the Keisanuma Bay Cross Bridge stands as the only bridge on the Sanriku Expressway that spans the sea. With a total length of 1,344 meters, it comprises 680 meters over the water and 664 meters on land. The height from the surface of the sea to the bridge girders measures 32 meters. The overwater section of the bridge takes the form of a cable-stayed bridge, where the bridge girders are suspended by cables fixed on the main towers. This design makes it the largest bridge of its kind in the Tohoku region of Japan. Illuminated at night, the main towers and cables add to the bridge's sleek and elegant appearance, creating a captivating sight for onlookers. The completion of the Keisanuma Bay Crossing Bridge in March 2021 marked a significant milestone in the recovery efforts following the Great East Japan earthquake. It not only provided a vital link for transportation, but also symbolized the resilience and determination of the residents of Keisanuma. The bridge's nickname, Kanae Ohashi, holds a deeper meaning. The term kanae is derived from the old name of Keisanuma Bay, kanae ga ura, while also serving as a verb meaning to realize. This conveys the passionate desire of the local community to achieve their dreams and hopes, even in the face of adversity. Beyond its symbolic significance, the Keisanuma Bay Crossing Bridge offers breathtaking views of the surrounding area. From the bridge, one can witness the scenic beauty of Keisanuma City, the bustling fish market, the majestic Kitakami Mountains, and the vast expanse of the Pacific Ocean in the distance. The panoramic vista serves as a reminder of the natural wonders and resilient spirit of the region. In addition to its aesthetic and symbolic value, the Keisanuma Bay Crossing Bridge serves a practical purpose as a life-saving road. The Sanriku Expressway was meticulously designed to withstand potential tsunamis and ensure the safety of its users. The devastating tsunami triggered by the Great East Japan Earthquake underscored the importance of infrastructure that could resist such natural disasters. With careful engineering and design considerations, the Keisanuma Bay Crossing Bridge was built to withstand the force of tsunami waves, safeguarding the lives of those traveling. The completion of the entire Sanriku Expressway in December 2021 not only connected Sendai City and Hachinohe City, but also facilitated improved transportation and accessibility along the coast of Iwate Prefecture. The expressway has become an essential lifeline for the region, providing faster and more efficient travel options for both residents and visitors. Moreover, it has become a symbol of resilience and recovery, showcasing the determination and spirit of the communities affected by the earthquake and tsunami. The Keisanuma Bay Crossing Bridge stands as an architectural marvel, a symbol of hope, and a testament to human resilience. It serves as a striking visual landmark and a vital transportation link for the Sanriku Expressway. The bridge's construction and completion have not only contributed to the physical recovery of the region, but also provided emotional and psychological support to the people of Keisanuma. The bridge serves as a reminder of their strength and determination to rebuild their lives and realize their dreams, even in the face of immense challenges. As travelers traverse the Keisanuma Bay Crossing Bridge, they are met with a breathtaking view that encapsulates the beauty and spirit of the region, reminding them of the indomitable human spirit and the power of unity in overcoming adversity. To ensure the safety of commuters and address the bridge's deteriorating condition, annual inspections had been conducted since 2009. The construction process progressed as planned in the new year. The contractor focused on processing and installing safety railings for the bridge, ensuring the safety of future users. Simultaneously, the installation of utilities, including water, electricity, and fiber optic lines, was underway and projected to be completed by mid-February. Other restoration activities, such as coastal habitat mitigation, tree planting, and retaining wall fencing, were also in progress. The bridge's scheduled reopening was set for March 1, 2022. At 2 p.m. on that day, the bridge would once again be accessible to vehicles. To mark this significant event, the city planned a ribbon-cutting ceremony at 10 a.m. in the morning, providing an opportunity to celebrate the reopening and acknowledge the completion of the project. During the construction period, a process called post-tensioning was employed to reinforce the bridge's structure. This involved installing 24 individual high-tensile steel cables within the bridge's box girder. These cables were placed in a conduit beneath the concrete surface and stretched to enhance the strength of the concrete. Additionally, efforts were made to classify the bridge's surface approaches appropriately. Following the post-tensioning process, the contractors would begin installing new access spans at the north and south ends of the bridge, which included the placement of 80 feet precast concrete beams. In an impressive display of engineering prowess, Sakanti and Ness Campbell joined forces to accomplish a challenging bridge girder installation project at the Ridgefield National Wildlife Refuge. With the aid of state-of-the-art cranes from Liebherr and Manitowoc Construction, these companies successfully completed the crucial task of placing the final bridge girders in position. This endeavor involved spanning the river and traversing the BNSF train tracks with the utmost precision and efficiency. The installation process was made possible by the deployment of two remarkable cranes, the Manitowoc MLC 300 and the Ness Campbell's Liebherr LTM 1500 and Grove GMK 5275. These cutting-edge machines, renowned for their robustness and capabilities, played a pivotal role in ensuring the smooth execution of the project. Beginning at the 26-second mark, the cranes swung into action, commencing the transfer of the bridge girder from Pier 1 to Pier 2. With meticulous coordination and advanced lifting mechanisms, the construction cranes maneuvered the girders with finesse, ensuring their accurate placement along the designated route. Continuing their feat, the cranes seamlessly transitioned to the next phase of the installation at 1 minute and 17 seconds. This time, their focus was on connecting Pier 2 to Pier 3. As the cranes extended their reach and lifted the massive girders into position, the precision and accuracy of their movements were evident. Every action was calculated to perfection, ensuring the stability and longevity of the bridge structure. At the 2 minute and 6 second mark, the cranes faced their final challenge, extending from Pier 3 to Abutment 2, spanning the BNSF train tracks. This delicate maneuver required utmost care and expertise to avoid disruptions to the train schedule while maintaining the structural integrity of the bridge. The cranes, under the skilled guidance of the operators, accomplished the task seamlessly, further solidifying their reputation as trusted partners in complex construction projects. The successful bridge girder installation at the Ridgefield National Wildlife Refuge stands as a testament to the exceptional capabilities of Liebherr and Manitowoc construction cranes. Through their synergy, Sacanti and Ness Campbell effectively utilize these cutting-edge machines to overcome formidable challenges, ensuring the completion of a critical infrastructure project that will serve the community for years to come. The construction and assembly process of setting bridge girders at night and pouring the bridge deck is a crucial phase in the Sumner Bridge project. With solid progress being made, the project is well underway. The bridge girders used in this project are remarkable in size, measuring 138 feet in length and weighing a staggering 125,500 pounds each. This equates to nearly 63 tons of weight per girder. Due to their immense size and weight, specialized equipment and meticulous planning are required to safely and efficiently set them in place. Setting bridge girders at night involves a coordinated effort of skilled workers, heavy machinery, and advanced engineering techniques. To ensure the safety of the workers and the integrity of the structure, the process is often carried out during nighttime hours when traffic is minimal. A team of experienced crane operators, riggers, and signalers work together to carefully lift and position the massive girders onto the bridge abutments and piers. Precision is key, as even the slightest misalignment can have significant consequences for the overall stability and functionality of the bridge. Once the girders are securely in place, the next step is pouring the bridge deck. This involves the placement and consolidation of concrete to create a solid and durable roadway surface. The deck serves as the uppermost layer of the bridge structure and provides the driving surface for vehicles. Pouring the bridge deck requires specialized concrete pumping equipment and skilled workers who ensure the concrete is properly mixed, placed, and finished. The process often involves the use of large concrete trucks and precise pouring techniques to ensure a uniform and high-quality deck surface.
Beam launching using a girder structure is a crucial process in the construction of bridges, and it plays a vital role in ensuring the stability and efficiency of the project. At Gamuda Garden in Rowan, beam launcher crane is employed to facilitate this operation. This specialized crane is designed to handle beams measuring 63 meters in length and weighing up to 114 tons. To ensure the safety and stability of the beam launcher crane, several requirements must be met. The height of the longitudinal running track on both sides needs to correspond to the required level to maintain stability. The horizontal running rails on the front, middle, and rear legs of the crane must be kept parallel, with strict control over the spacing between them. Additionally, the 3 rails must be maintained at a horizontal level. During the installation of concrete beams for skew bridges, the position of the front, middle, and rear legs of the bridge erecting machine should stagger. This allows for the staggered positioning of the left and right wheels, enabling them to run on the same horizontal track. The spacing between the wheels can be calculated based on the skew angle of the bridge, ensuring smooth movement. The longitudinal movement of the bridge machine must be carefully planned and executed without any interruptions. It is crucial to avoid stopping halfway during the operation. To enhance stability during the longitudinal movement, the front leg of the crane needs to be tightened and fixed with the hand hoist and transverse rail. When dealing with bridges that have vertical slopes, measures must be taken to prevent sliding during the longitudinal displacement of the bridge machine. Triangle iron blocks can be used to protect the front and rear of the wheels. Special attention should be given to the middle leg, which is in close proximity to the beam end, and careful control is necessary during shifting. During the installation operation, running the crane in overload is not allowed, and lifting operations must be carried out without any inclination. The viaduct over the Tagus River for the Avenue, located in Spain, is an impressive engineering feat that forms part of the Madrid-Extremadura high-speed railway line. This viaduct, managed by ADIF Administrador de Infraestructuras Ferroviarias, spans a length of 6.5 kilometers and represents a significant investment of €64.85 million. It is designed to accommodate mixed traffic with a double track of international gauge and a platform width of 14 meters. The most remarkable feature of this viaduct is the large concrete arch that allows it to cross the wide expanse of the Tagus River without the need for additional piers over the water. The viaduct's alignment consists of a long curved section followed by a straight section, with the spacing of the spans influenced by the crossing over the Tagus River. The deck over the arch is divided into 6 spans of 54 meters each, all of which are supported by the arch. The approach spans leading up to the arch are 60 meters long, with 2 transition spans of 57 meters on each side of the arch's starting point. This arrangement provides a harmonious and suitable distribution for the 26 spans that comprise the viaduct. Undoubtedly, the most iconic element of the bridge is the arch itself. It spans an impressive 324 meters between supports and rises to a height of over 17 meters above its foundations, reaching 90 meters above the average level of the reservoir. This arch is set to become a global reference for viaducts of its kind in railway construction, surpassing the current record span built in Spain and ranking among the largest in the world. The arch is constructed using a flat and hollow rectangular box girder section with a variable depth. At the base, it has a width of 12 meters and a depth of 4 meters, which gradually reduces to a width of 6 meters and a depth of 3.5 meters at the crown. The deck, on the other hand, consists of a prestressed concrete box girder section with a constant depth of 4 meters. The lower width of the box is 5.6 meters, which increases to 6.5 meters at the top. Additional cantilevered sections on each side of the deck help achieve a total width of 14 meters. The height of the piers varies to adapt to the terrain profile, reaching over 72 meters in the area closest to the river crossing. All piers are constructed using a single hollow box section, except at the abutments, where the section is solid to accommodate the loads transmitted by the deck. One noteworthy aspect of the construction of this viaduct is the use of high-strength concrete, with a strength of up to 70 megapascals. This ensures the durability and stability of the structure, even under the significant loads and stresses imposed by the railway traffic. The construction process for this viaduct begins with the execution of the foundations, which are solved through large direct footings on the rocky substrate to distribute the considerable loads they must support. In the areas affected by the arch, plinths are constructed for the starting point, and retaining footings are built for the adjacent piers. To enhance the ground stability, cement slurry is injected to fill any existing fractures in the rock mass and minimize potential deformations and settlements. To enhance the ground stability, cement slurry is injected to fill any existing fractures in the rock mass and minimize potential deformations and settlements. This improvement process necessitates the injection of over 300,000 liters of slurry under pressure through more than 7,000 meters of drilling in the rock mass. Once the foundations of the viaduct over the Tagus River for the avenue are completed, the construction of the pier walls in the approach spans on both sides of the river begins. To facilitate this process, climbing formwork systems are employed, allowing for efficient and systematic construction. Climbing formwork systems consist of adjustable formwork panels that are securely attached to the previously constructed section of the pier wall. These panels provide a framework for pouring and shaping the concrete. The formwork panels are designed to be easily climbed upwards as the construction progresses, typically in 6-meter sections. The process starts by fixing the formwork panels to the completed section of the pier wall. Reinforcement bars are then placed according to the design specifications. Once the preparations are complete, concrete is poured into the formwork, creating a new section of the pier wall. After allowing the concrete to cure and gain strength, the climbing formwork is raised to the next level, and the process is repeated. Climbing formwork systems offer advantages such as providing a safe working environment, as the formwork panels are securely anchored and serve as stable platforms for the construction workers. They also enable faster construction progress, as the formwork can be easily repositioned once the concrete has cured. The use of climbing formwork ensures consistent and accurate construction, resulting in uniformity and structural integrity throughout the viaduct.